In this video, we're going to apply our new technology for evaluating improper integrals, or integrals that involve infinite quantities. And we're going to use that through or on a series of examples to see how it works in practice. So in this case here, this integral is clearly improper because of the infinite limit here. The first, non-optional, obligatory, cannot skip step is to apply the definition. What do we mean by putting an infinity here instead of a number? It means that we really should have a value up there. Typically we use b, and the 1 stays the same. Once we've done that substitution, we follow up by asking what would happen as we take that limit, that upper value for our interval, and take the limit as it approaches infinity. So again, the concept is we have some graph. When one fixed point is at 1, that's fine. We want, in principle, the area underneath this graph all the way out towards infinity, but we can't calculate that in one step. So we take an intermediate step where we cut that off at some value b, find the area there as a function of b, and then let b go to infinity. This area is finite and depends on what the b value is. Then we can push the value b out to larger and larger values. All right, then we put in our expression here. If we're integrating, it makes sense to write it as a power, t to the negative 2. So what we could do during the calculations is we just keep copying this down. We want to evaluate this entire thing, which will be equal to the same limit, asking the question what happens when b gets larger, but we have to evaluate the integral first, so we just keep copying this down line by line until the very last step. We now look at our integral. T to the negative 2, we know how to integrate that. Add 1 to the power, divide by the new power, and the upper and lower values will be b and 1. Copy the limit again. Here we're just going to tidy up by subbing in t equals b and t equals 1. That will give us negative 1 over b minus negative 1 over 1. And then we'll tidy that up. Makes it easier to evaluate the limit, which we've just been copying along all the way down here. It's the last thing we apply. This here becomes 1. We write it first, and then negative 1 over b is the second term. Now, there are no integrals left. So this is literally the area that we're talking about, between 1 and b. If you tell me what b is, we'll be able to tell you what the area is. And then we're able to ask now, what happens as we push b towards larger and larger values? This goes back to earlier work in the course. If we make b larger and larger, 1 over b heads towards 0. And so this is simply 1 minus 0, or 1. We would also then say in the terminology here, this integral converges as opposed to diverges to the value 1. Let's take a look at a second example. Same form of integral, almost the same integrand. Remind yourselves the first thing to apply is the definition. If we see this improper integral, this infinite quantity, we integrate it not from 1 to infinity, but to 1 to some other value, some variable that we're going to use later. And then we are going to remind ourselves to push that upper limit towards infinity as a second step. We won't rewrite this integral here because we actually have a form that's special for 1 over t. Unlike all the other powers of t, this is going to give us ln of the absolute value of t. And again, we just copy the question or the statement that we need to let b go to infinity, each line by line. Our upper and lower values that we're going to sub in are b and 1. Copy the limit here down. We're going to have ln of b minus ln of 1. All right, we can tidy that up. This is actually just 0. So we'll have the limit as b approaches infinity of ln of the absolute value of b. So now we're asked what happens to ln of b as we put in larger and larger values of b. This in fact heads towards infinity as well. The ln graph, if you go back to the basic functions that we've learned, the ln graph flattens out, but it still does grow forever and can get infinitely large. And so this limit does not exist. Need to add some space here. And if the limit does not exist, then the terminology we would apply here is that the integral from 1 to infinity of 1 over t dt diverges, as opposed to converges. There we are. So the process is exactly what you've learned before. We do integrations, but then we have a flashback to earlier in the course where we evaluated limits, but we only do that as a separate thing once we've completed the integration step. Having looked at two cases with different outcomes, let's take a look at the graphs of each of those functions and see if that helps us understand what's happening here. The first graph we drew, or that we integrated underneath, was the graph of 1 over t squared, whereas the other graph was 1 over t. When we sketch those out, we can do that fairly quickly here. 2 squared is 4, so we'll have 1 over 4 as a quarter, and so we'll have a graph that looks like this. And on the other side here, when t is 1, we'll be at 1, then we'll have a half, then a third, then a quarter is there. So this graph looks like this. Let's clean this one up a bit here too. There we go. And what we were computing in both cases was the integral from 1 to infinity of that function. In this case, 1 over t squared. And that represents the area underneath the graph going out towards infinity. And likewise, the integral of 1 over t from 1 to infinity with respect to t is the area under this graph. So take a look at that for a moment, and then ask yourself, how much does graph sketching help in analyzing these types of integrals? Pause the video for a moment, and then we'll check in. All right, I think for most people, this is one of the rare times in calculus where a graph sketch really doesn't help at all. If we hadn't annotated these pictures and known that this area here was finite, whereas this area here is infinite, then the graph wasn't going to give us more information. And the reason for that is all the interesting stuff is happening down towards the limit as t goes to infinity, or as b goes to infinity, as we increase the area or the interval size. In other words, sketching here really isn't that much of a help. That's why we have to focus, going back a page, on carefully looking at the integral itself and then using that definition of the limit, changing the upper or lower ends of the integral to help us evaluate these. We have to be very, very careful about it. Graphing is not going to be a sophisticated enough tool to really help us here.